Take a line, any line that goes straight up and down, like this. Now draw another line that intersects that line at an angle, like this. If you can imagine for a second that this pair of lines was in 3D space, rotate the angled line around the fixed one, keeping the angle between the two lines constant. Done! Now you have a cone swept out by the rotated line, which consists of two naps, or the two half cones, one on the top and one on the bottom, joined tip to tip, and they can be sliced in a variety of ways. If you sliced it perfectly horizontally, the cross-section you would get is a circle and would look something like this. Slice it at a slight angle and you get an ellipse, which would look something like this. Slice it at any angle steeper than one of the generators, which are the two lines that cross at the tips of the naps, make the same angle as the angled line we started with, and like this, and you get a hyperbola consisting of two separate curves. You can also slice it directly through the point where the naps touch, but that is kind of pointless. Or not pointless, since all you get is a point. But if you slice it exactly parallel to a generator, the cross-section you get will be a parabola, and parabolas are interesting shapes. It is a curve you may remember from when you learned about quadratic equations in Algebra 1, or when you learned how systems of equations can be used to graph a parabola using only 3 points. You also may remember they can be written in the form of ax squared plus bx plus c equals 0, with the vertex of the parabola, the point where the graph is at a global minimum or maximum, at negative b over 2a, f of negative b over 2a. The variable a represents how stretched or compressed the parabola is. The variable b represents horizontal movement of the axis of symmetry without affecting the y-intercept. Finally, the variable c represents vertical shift. In addition to the quadratic formula form, parabolas can also be written in their standard form. Just like the quadratic formula form, it always involves a squared variable term, giving the parabola its distinct curve shape. The standard equation of a parabola, assuming it opens left or right, is y squared equals 4ax. If it opens up or down, x and y are swapped. I'll explain what a means in a bit. Keep in mind this equation only works for parabolas whose vertex is at the origin, but I will cover that later. If a is positive, then the parabola opens upward or rightward, depending on the equation. If a is negative, it opens leftward or downward. In addition to just being the shape you get when you slice a cone a certain way, a parabola can also be defined as all points are the same distance away from a fixed point, called a focus, and a fixed line, called the directrix. The directrix is always parallel to the tangent line to the vertex of the parabola. The axis of symmetry, which is the line that splits the parabola in half, is perpendicular to the directrix and passes through both the focus and vertex. And finally, we can get to what a is. It is the distance from the vertex of the parabola and the focus. For the equation I said to work, the vertex has to be at the origin or else it doesn't work. The parabola will be shifted if the vertex isn't at the origin. For a parabola that opens left to right, the focus will be a0 for rightward and negative a0 for leftward. For a parabola that opens up or down, it'll be 0 plus or minus a. Speaking of which, the latus rectum of a parabola is the line parallel to the directrix that intersects the focus. It helps drawing the parabola, as it always connects two sides of the parabola. The length of the latus rectum is always 4a, regardless of which way the parabola opens. The directrix will be x equals negative a for a rightward parabola, and x equals a for a leftward parabola. For an upward or downward parabola, it'll be y plus or minus a instead. Remember how I said that the above formulas only work for parabolas whose vertex is at the origin? What about parabolas whose vertex isn't 0, 0? This is where we throw in the vertex hk and adjust our formulas accordingly. This is equivalent to shifting the parabola rightward h units and upward k units. Now the formula for a parabola is x minus h squared equals 4a times y minus k for a vertical parabola, and y minus k squared equals 4a times x minus h for a horizontal one. Now the focus of a rightward or leftward parabola is now h plus a k or h minus a k, respectively, and the focus of an upward or downward one is h k plus or minus a. The directrix changes as well, being x equals h minus a for a rightward parabola and x equals h plus a for a leftward one. For a vertical parabola, it is y equals k plus or minus a. This makes sense. After all we did was translate the parabola, not stretch it or compress it. Another interesting fact about parabolas is a property called eccentricity. Eccentricity is a measure of how circular a curve is. An eccentricity of 0 represents a circle, whereas any eccentricity between 0 and 1 gives an ellipse. An eccentricity above 1 represents a hyperbola, with an infinite eccentricity representing a straight line. Meanwhile, an eccentricity of exactly 1 gives a parabola. Now why does all of this matter? First of all, the focus of a parabola has another interesting property. All parallel rays of light that enter the parabola parallel to the axis of symmetry will converge at the focus. 3D paraboloids, formed by spinning a parabola in 3D space, have very similar properties to parabolas except for the fact that they are, obviously, 3D. Many 3D structures, such as radio dishes, reflecting telescopes, searchlights, and even parabolic solar cookers, will be designed with this principle in mind, where the light source or food will be located directly at the focus for maximum effect. Parabolas also have other uses in physics, particularly in projectile motion. Want to find the path of a football in flight? Use parabolas. Want to determine the path of a cannonball or bullet? Also use parabolas. In fact, the path of almost any object that is launched, shot, or thrown into the air can be graphed using a parabola. Here's a video of parabolas in action demonstrated by me shooting a basketball. As you can see, the acceleration of gravity gives the parabola its distinct, ever-steepening curve shape and allows me to make the basket. Parabolas also have plenty of uses in architecture. The Eiffel Tower, for example, has 4 arches that form the legs of the structure, making it very strong. The same goes for arch bridges, which are sometimes catenary curves, but other times parabolas. Even sand dunes in nature are often parabolic, as shown here.